Water is leaking out of an inverted conical tank at a rate of 10,000 cubic centimeters per minute. At the same time that water is being pumped into the tank at a constant rate. The tank has a height of 6 meters and the diameter at the top is 4 meters. All right, I'm going to pause there and start drawing my picture. Okay, so we've got an inverted conical tank, which just means that it's not sitting on its base. So the point is down. And it says that the tank has a height of 6 meters. So that's going to be the entire tank height here. Can I do this sideways? Let's see, 6 meters. And the diameter at the top is 4 meters. Okay, so all the way across at the top, diameter is 4 meters. And it says the water is leaking out of the tank. So we got water coming out. We know how fast the water is leaking out. 10,000 cubic meters. Okay. But it says water is being pumped in at the same time. So here's the problem. The 10,000 part that we were given, the rate we're given, which is the 10,000 cubic centimeters per minute. A lot of people want to write that as their dV/dt, but that's not going to be the rate at which the volume's changing because we're pumping water in at the same time. So we have to consider the fact that water is getting pumped in, but then water's also leaking out. So this is not going to be the rate of change of volume. So this is just the leak. So I'm going to call L the leak. So I'm just going to label this as DL. How about that? DL dt. I'm going to use a capital L just for right now to recognize that that's going to be the leaking rate. All right, moving on. It says if the water level is rising at a rate of 20 centimeters per minute. So let me draw in my water's rising. Okay, so clearly I'm going to be pumping water in at a larger rate, a higher rate than 10,000 cubic centimeters per minute. In order for the water to rise, right, the rate at which I'm pumping water in has to be bigger than the rate at which it's leaking out. So if the water level is rising at that rate, so let me go ahead and get some more variables in here. The water level is rising. So I don't know whether you want to call this H or W. It's not going to really matter. So my water height, I'm going to use W. So W is my water height. So it says that my rate at which the water level is rising, so that's dW dt, and it's rising at a rate of 20 centimeters per minute when the height of the water is 2 meters. So dW dt is equal to 20 centimeters per minute when the height of the water, which I have labeled as W, when W is equal to 2 meters. Find the rate at which the water is being pumped into the tank. All right, so I'm going to find the rate at which the water is being pumped. I'm going to use P for pump. So dP dt is what I'm looking for. So let's talk about the rate at which the volume is changing, okay? So the volume is changing as I pour water in, but then I am leaking water out. So if we think about the actual rate of change of volume, it would be the rate at which I'm pouring the water in, which is dP dt, but then I've got to subtract out the leaking rate, and the leaking rate is the dL dt. So we've got like the rate of the pour minus the rate of the leak. And dL dt was given to us, right? We know that. We know that is 10,000 cubic centimeters per minute. So dV dt is equal to the rate of pour, dP dt, minus 10,000. All right, I'm going to pause there and I'm going to go to Emily or anybody else. Are we okay so far on this setup?
Yeah, I'm good where we are.
Okay, can anybody see the immediate problem though that I'm going to have with units right here? Anybody want to chime in and looking at your units? Why this is one of those, remember I warned you that the book was going to mess with you a little bit on units for one of these?
It's meters to centimeters.
Yeah, exactly. So we have to make that decision. Yeah, see how we have the height of the cone measured in meters, so is the diameter, and yet these rates that were given, they were rates in centimeters. So you kind of just have to make the decision whether you want to commit to doing the problem in meters or whether you want to commit to doing the problem in centimeters. If you want to do it in meters, then you are going to have to convert these rates, 20 centimeters per minute and 1,000 cubic centimeters per minute. You'd have to convert those rates to meters per minute. So that's one option. Or if you're going to convert everything to centimeters, then you just have to convert the 6 meters and the 4 meters and this 2 meters. You have to convert those to centimeters. Doesn't make a bit of difference. You can do it whichever way you choose. Some people find it easier just to convert the lengths, So like if let me try that again. So if W is equal to 2 meters, well then we know, multiply that by 100, so we know that this is going to be 200 centimeters. And then up at the top, if the diameter was 4 meters, right, 4 times that, that's going to be 400 centimeters. And then the 6 meter height is going to be 600 centimeters. So some people find that conversion to be the easiest, just to convert everything to centimeters. We are going to get really big numbers because we're talking centimeters versus meters. If you prefer to go the opposite way and convert to meters, that's fine too. Okay, so at this point, we've got to kind of get our bearings with variables because we got a lot of variables floating around here. So I have this equation, dv dt equals dp dt minus 10,000. So the two variables there are v for volume and p, which is the rate of the pour. And we have to keep the pour rate because that's what we're looking for. But dv dt, we may be able to find that out because we do know the equation for volume. So I would start here by focusing on the dv dt, since we have a volume formula for a cone. So again, this is one where you wouldn't have to memorize the volume of a cone. I would give this to you if I give you a problem on an exam that involves a cone. So we know that the volume of a cone is 1/3. And again, if you look in your textbook, it is in the textbook on the reference pages as well. So the volume of the cone is 1/3 pi r squared times the height. Okay. So now pause. We need to take the derivative of this, but we've got to decide, should we eliminate any of these variables? So like, do we want v, for example? So do we want v? And the answer would be yes, we need v because dv dt is in this equation up here. Okay. And then you go, well, do I want r? Well, do I have any information in my work here about dr dt? And the answer there is no. I see no information about r. And then what about h? Now h was the height of the cone, and actually let's relabel that so this is correct. According to our picture, I shouldn't say the height of the cone. Let me rephrase, the height of the water, right? The water level. So I really should actually get rid of that. I'm laughing because I don't think it's letting me eliminate it. There we go. So I want to replace that. Instead of h, I'm going to label that as w. So then, do we want to keep w? The answer is yes, because we have dw dt up here. So yes, we want to keep w. So before we go into our derivative, this is another one where we need to eliminate a variable, and the variable we want to eliminate is the variable r. We need to eliminate r. So going back to our picture, we don't have the radius of the water labeled. So let's go back up to the diagram and label that. The radius of the water right here, which is changing as the cone fills up, the radius is r. So if you take a look at the right triangle that we have a little right triangle here. I'm just redrawing it off to the side with the water height and the radius. But then if we continue up in our diagram, go all the way up to the base of the cone, we have this larger right triangle And we know the height of this triangle is 600 centimeters. And then the radius we have to figure out because we labeled the diameter, right? The diameter of our cone's base was 400 centimeters. So the radius in this case is going to be 200. So in order to eliminate r, we're going to have to use similar triangles and set up a ratio and then a proportion. So the ratio of the radius to the water level in this case is going to be 200 to 600. In other words, the ratio is going to be 2 to 6, which is a ratio of 1 to 3. So then we can go ahead and cross multiply. So that'll be 3r is equal to 1w. But then remember, we're trying to eliminate r, so we're going to go ahead and solve for r by dividing by 3. So r is going to equal w divided by 3. However, I'm going to leave that as 1/3 w. Because then I'm going to be able to go ahead and substitute that here into my volume equation. And I will have successfully gotten rid of the variable r. So 1/3 pi, it used to be r squared times w, but now I'm inputting 1/3 w here in place of r. So from here, you're going to have to simplify. So we want to simplify as much as possible before we take the derivative. So 1/3 squared will be 1/9, and then w squared, but that's multiplied by another w. So 1/3 times 1/9 will be 1/27 times pi times w cubed. So now I'm ready to take the derivative of both sides with respect to time. So I'm taking the derivative of the left side of volume, and then I'm taking the derivative of this right side, which with the derivative of 1/27 pi w cubed. So the derivative of volume with respect to t will be dv dt. And then again, the 1/27 pi is our coefficient, so I'm just going to leave it. It's a constant multiple. And then the derivative of w cubed will be 3w squared. But then chain rule says I'm going to have to chain on the derivative of w with respect to t, and that's where the dw dt comes from. So if I simplify here, 3 divides into 27, 9 times. So dv dt will equal 1/9 pi w squared times dw dt. So now I can go back up and input the information that was given to me. Where did it go? Way back up here. So I'm looking at dw dt was equal to 20 centimeters per minute when w was equal to 200 centimeters. So I need to input those values down here. That will give me the value for dv dt, and then this is where I'm going to have you guys finish it on your own. If you look back at our equation that related the pouring rates, which is right here, so then I will have dp dt, and then, back it up. I will have dv dt, so then I can solve for dp dt by adding 10,000. Essentially, and then that will let me solve for dp dt.